Oh, this one. Yeah, just fine.
I kind of changed myself into that.
Yeah, don't close that door.
And following the section of subreferences, my house starts all really, really hot. So I put my leg into effect, let go of everything around that, let all kinds of hot water and cabin control to test you right over a Bunsen burner without realising it's sulfuric acid. Straight through that. I was always paired with the most competent one in the class for experiments, and I always had the one sitting taking the notes while he single-handedly did all the stuff in the class.
Or is it that one?
All right.
Awesome.
Seems like a very low turnout. I shall begin. So, good evening, everyone. Today is our last talk for this term, and today we have Dr. Stephen Hicks, who is a research fellow with the Nuffield Department of Clinical Neuroscience. And he is working on developing a pair of smart glasses that will help near-blind people significantly improve their vision. So, without further ado, Dr. Hicks.
Thanks very much. Thanks for everyone who came along. Thanks Leon and Roy for an entertaining dinner and a wide-ranging conversation. As Leon said, I work in the Nuffield Department of Clinical Neurosciences as a research fellow there. I've been running a project for the last 3 years to develop a wearable visual aid for people who are registered blind. The idea is essentially put out here in the graphic on the side, which is the idea that you want to have some kind of, if you've only got a small amount of sight, obviously a lot of different tasks become quite difficult, reading and face recognition, things like that, which I'll talk about in a moment. But one of the classic problems people have is mobility, recognising where obstacles are, what kind of things you can interact with. Using a lot of modern computer vision techniques and wearable systems, we can actually produce a display which is quite easy to be seen by people who are visually impaired. And the idea is that we can put this into some kind of form factor which is aesthetically pleasing, because nobody wants to look like you've got most of a robot on your face, and something which is scalable, and you can start putting some of the really interesting stuff that comes out of computer vision into an augmenting system to help people around. There's obviously a lot of people who pay for the research, which is very nice, and there's people, some people who are computer vision scientists, some people who are clinicians, and we've sort of come together as this multidisciplinary team to really kind of understand, first of all, what people need, and then how we can put that into practice. It's a nice small group. If as I'm going through, there are things that pop in, do you mind, that you'd like to discuss? I'm really happy to entertain that at the time. So whatever you like to do, we can just pass the tangle of the story. So I'll mostly be discussing the general ideas about what we do with smart glasses, some of the considerations that we go into designing them, how to make them with modern day technology, and also some of the backstory about why this is important, what other stuff's been done in the area, so you can get a general feel for where it's at. So I think the first thing to really understand is really what people mean when they talk about blindness. So obviously the classic idea about blindness is you have no level of sight. But there's only about, out of all the people in the UK who are registered blind, there are about 5% of people, under 30,000, who are actually, far less than 30,000, 15,000 or so, who actually have no light perception at all. There really is, there are levels, there are techniques you can use to do it, but basically the RNIB and a lot of other people adopt a general description that if your sight level has gone too low, that a normal task that requires vision is now impossible, or without some kind of assistance. There are a very large number of people who are registered blind in the UK, 300,000 or so, and this kind of scale is relatively similar across different countries. So there is, in terms of, I often talk to people about marketing and spin-outs and things like that. There's a good market. There's a lot of people who can use this sort of technique. But most people have some light perception. There are three main ways in which you lose your sight, and by far in this country and many others, macular degeneration is the key one. You've got your visual field, loosely represented as a square there, and you get a scotoma, which is a blind spot, generally expanding from the centre and expands out. Often this is age-related. It's mostly you can maintain the disease progression, but it's uncurable at this stage. And a lot of people, it's very, very hard to understand what's actually going on with the damage to the retina. So recovery and rebuilding your retina from macular degeneration is very important. It accounts for over half the number of people who are blind in the UK, and generally geared towards people who are older. On the opposite side, you have something like glaucoma, which is quite common as well. In this case, you lose peripheral vision and gradually encroaches in. So these two are really vastly different in terms of what you can achieve. The central part of your vision is called the fovea, and that's where you've got all the high definition for reading, recognising faces, things like that. But the periphery is really key for mobility and understanding your general sense of awareness. On the opposite side, glaucoma, you've lost your peripheral vision, you've lost your ability to orient yourself, but you do often have a small window which you can read letters. As it progresses, that window gets smaller and smaller. Once it gets beneath about 15 degrees, you become legally blind. And that means you can no longer really read more than a word at a time, and that's obviously a problem. And recognising things that are outside of the centre of your field of view is impossible. To finish off the three main types, we have one called diabetic retinopathy, which is essentially a mixture between the two. You get blind fields occurring at random spots, and they expand as the capillaries underneath the retina start to bleed and produce scarring. This can be halted by laser treatment, but again, it can't be reversed because the retina is such an intricate thing. I'll talk a little bit about retinal prosthetics in a moment, but there's no good way to try to repopulate that with, say, stem cells. That actually makes sense. Partly because the brain has already learnt to associate the topography of the retina with what's actually happening in the outside world. So if you reintroduce stem cells into the either retina or in the optic nerve behind it, you won't match it up with what you've learnt through your childhood development. So the three main issues that people face, and this is in order, reading is the primary one. Everybody hates to lose their ability to read, especially when you get older. But reading for pleasure, reading signs, reading newspapers, all that becomes such a difficulty. Right. But then socially, the next one is recognising faces and recognising familiar people. So there's a lot of missed social interactions by people who have got visual deficits because you just don't know your friends there, you don't see them when you do things like that. Recognising expressions in conversations if you want to. The area that I got into most of all was mobility, or what we call independent travel there. And that's where we classically see things like the white cane and the guide dog being used. So there are assisted technologies for mobility. The cane being the main one. There's between 60 and 70,000 people who use canes in the UK. But the guide dog, even though it's quite a prevalent technique, there's somewhere around about 7,000 guide dogs in action in the UK at the moment. The same amount actually in the US, given that there's 8 times more people. Still the same number of guide dogs. Most of that is because of the gigantic cost. The total cost for training and lifespan of a guide dog is about £50,000, of which the end user pays £1, at least in the UK. And hence the guide dog charity. Always looking for money, always to produce more guide dogs. Most people go for personal assistance, or actually, once you get older, most people don't go out. And there are other techniques such as audio substitution. So you get a camera, try to get it to describe the world in front of you. Often this just turns it into a series of tones and pictures that will represent the visual world in a way in which you can pick up visual hearing, which is, I've demonstrated that in a couple of talks, but it's just awful. The experience of turning a grayscale image into sound is just, it's difficult to listen to, it's very, very difficult to learn. So where I got to this question, so I didn't give any background on myself, but I did a PhD back in Sydney on the hippocampus and spatial navigation. I've always been interested in what goes into making our complete worldview. Like how can you have such a stable, colour-filled, high-detailed worldview when you've got this tiny fovea, a limited amount of time to look at it. And so I've always been fascinated about how we build that up. So I like working with visual displays and exploring different ideas about that. And then when I joined the John Radcliffe, I joined Oxford. Actually, I was in Imperial before that. We did a little bit of work on this before. It's just trying to see if any kind of virtual reality and real-time camera technique can help describe the world and allow us to understand experimentally what the elements are, or what sort of things you can use to understand key parts of our environment. And working in a hospital, everyone always wants to do something clinical. So after a little bit of time, we turn towards visual impairment as a way to look at that. So I started to learn more about visual impairment and realised that most people have some sight. Everybody who makes an assistive technology, such as a cane or a dog, an audio substitution or a personal assistant, they don't consider any of the sight that remains, because you think, why would I make smart glasses for blind people? It doesn't make any sense, they can't see it. But it turns out that almost all of them can, and there's a lot you can do. So I'm not the first person, obviously, to work in this area, building up displays, but all the ones before it had either limited in terms of their technology, because they've been done before the age of mobile phones, so you can't carry around a personal computer, or they've been really seriously aesthetically challenged. And I think that's not an insignificant point. So the power boy for augmented vision is Jordan Forge. He carries around his multispectral visor, and he's actually totally right, and goes straight into his optic nerve and you can see all the things. But that's what people think when they think about augmented reality or augmented vision for visually impaired people. And in fact, NASA at the end of the 80s or the early 90s developed their own system they called Geordie, which was a camera system with a virtual reality display behind it. And essentially all it would do would magnify and increase the contrast a little bit, which allowed people who had low vision, rather than registered blindness, the ability to see a little bit more about the environment. I mean, the problem is, well, it's limited in its functionality and it's not an attractive thing. At the end of last year, a Canadian group produced, called eSight, they produced basically a similar technique, but using modern day techniques. So it enhances, it stretches out the colour space, it can allow people with limited sight to see faces again, particularly in photos. Again, I just don't think it's something you can wear outside. It just interferes with your communication. You can't see each other's eyes. Even if one of the people isn't so great at seeing another person's eyes, it's still quite important to have that. So I just spent a lot of time thinking about whether you can make something which is socially acceptable, whether you can have something which is portable and carry along with you, and it's not going to be off-putting for other people when they come face to face with you. Also, this costs $14,000, and it doesn't take very long to guess that the majority of people, well, a lot of people who are sight impaired won't have a great deal of disposable income. So $14,000 is not a great price. So one of the motivations I've had as well is to not necessarily use the cheapest thing I can find, but use things that are readily available in order to make something which is really cost effective. So I'll take it back a step after this and talk about where I began this idea, because it sort of lends itself to where we got to. So when I was doing my PhD, I became really fascinated with, actually I was really interested in cybernetics, prosthetic devices and brain-machine interfaces, because it's always so interesting. And the only really working version of that is the visual prosthetic. There are cochlear implants, but the visual one provides you an external visual experience. So at the hospital, we've done a trial on implanted prosthetics. Now this may be, you've probably heard about the idea, but let me tell you a little bit about how it works. In a particular type of eye condition called retinitis pigmentosa, which is about 6% or so of blindness, a lot of the retina is still left intact. You lose the very back, which is the photoreceptive cells. But at the front here, you have these things called ganglion cells, which are really just, they're very large nexus type objects. They'll take in input from thousands of individual photoreceptors, summate it, and then send it out to the optic nerve back into the brain to produce sight. They're relatively robust. So in certain diseases, they'll remain even after all the light detecting cells are gone. So the person has the experience of blindness, but they've actually got a lot of the underlying mechanisms still intact. So if you slip an electronic stimulator right into interface with the ganglion cells and produce bright flashes or bright electrical pulses, you can produce a phosphate that will be spatially locked to your retinal space. So then all you have to do then is expand it out to an array, get as many of these as possible, and you'll be able to produce something which is similar to this. This is a 30 by 30 retinal prosthetic, which is about the maximum people have been able to do. And if you happen to have the face lined up right on top, you'll be able to get some contrast and get the experience of sight, which sounds miraculous. It's been done since the mid-80s. Sometimes cortical implants, sometimes straight in the optic nerve, but mostly in the eye, because it's the easiest place to really do these things. But for a long time, and still really now, the resolution's been so low that there isn't really much you can tell. And you're using natural light as your input. Bright lights will come up as spots, but ambiguous shapes will always disappear. So I really like the idea of interfacing machines and human sensory system, but I've always thought it was very, very limited. Let me show you a nice little video of how that works, because it's produced by the company that do the retinal chip that helps it. So it slips very neatly. Obviously, the eyes are already been cut in half, so it makes it even easier. It slips into the back. This one's quite nice, because all it does is it takes natural light coming through the cornea, and small sensors on one side are able to transmit, able to take the stimulus from the incoming light to trigger an electrical impulse, and that goes into the ganglion cells and firing out into the optic nerve. It was a relatively simple idea. There are several different approaches to it, but that's generally the way. There's been some people who've been able to deal with this very well. So this was a German patient who had retinitis pigmentosa, who was completely blind. And within the week of getting his implant, he was able to detect primarily the shape of objects and have a good guess. So does it sound that there's subtitles at the bottom, so it makes sense. And really using his intuition and the small number of pixels that are lighting up, he's able to see the shape and guess a lot. You've got to use a lot of context in order to make this work. You need a lot of light, hence the high contrast environment he's doing it. Completely black table. It's actually a very bright light above the top, and that gives you enough of the enough input to work out the shape of the object. So he's got sight perception. Yeah, he's able to use he's able to determine what that object is. But it's very limited. So the trials that have been done here have been able to show people can tell doorways, a little bit of navigation improvement. But as soon as the light goes down, there's nothing you can do. There's no sophisticated computer vision going on with that. I guess one of the things that I've thought about is that the analogue to this is the cochlear implant. So I don't know if you know much about this area, but it's one of the real success stories for prosthetics is getting the sound, getting hearing back from the cochlea. The cochlea is simply a linear sensor that has a range of frequencies it's able to detect. Over 20 or so thousand hertz. The cochlear implant just puts a strip of electrodes into the cochlea with 20 odd electrodes and is able to produce enough of a range of sound to get conversational hearing back. It's terrible when you've got a high range of stuff, so music sounds bad, things like that. But with a very limited apparatus, you're able to get really functional hearing. And the question was, why don't you get the same sort of thing for a retinal implant? You've got roughly the same proportion of light-sensitive cells and electrodes, but people find it, you get a really small window. And essentially it kind of comes down to two things. One is that the cochlear implant spreads its stimulating repertoire or range over almost the entirety of human hearing, and the brain can piece it all back together. Whereas the retinal implant necessarily is a small square. It's not going to give you a full field of view. And secondly, there's nothing. It's a different type of thing. It's not. Sight isn't just a single stream of varying data. It has has colour. It's got a lot of processing going on in the retina to resolve edges. It's not. You need to help the retina out a lot. So where I kind of got into that is what ways can you improve on the retinal implant? How can you make it better for people? And what it typically really comes down to is doing something with the image, pre-processing it so you can identify key parts first of all. If you've only got 1,000 or so electrodes, you don't have a big screen to represent this. And the other one is field of view. And you can't do that with the implant because you've got these tiny chips. You can't put a spherical array in the back of the eye, at least not yet. But you can stick it on a screen. So that's what we're going to work at. We did a small project in 2010 where we just got computer was detecting simple objects. We had a very seriously sight impaired guy who's put on his VR goggles, and they asked him first of all, whether he could see these signs in the environment. It was a simple one to get right, and obviously he couldn't see smiley faces and hates printed up on the wall because he was almost totally blind. But then we got the computer to detect those and turn them into bright reaches of light on his head-mounted display. Then as he turned around, he goes, "Oh yeah, that's pink, that's a number 8, that's yellow, that's a smiley face." So the proof of principle has been able to codify aspects of the outside world into something which people can see. Seems completely feasible. You can detect objects. I can turn them into I can abstract them into ways which people can see. But the problem really, because of way too naive, still marginally naive, but even more naive back then, is that you can't codify everything in the world. You can't simplify them all down. Someone made a nice practice trying to get a computer to recognise all things in the world. Object recognition in a practical sense right now is very, very limited to faces, simple things like that. And is even real-time object detection actually what people need in order for improved functionality during the day? There's a lot of great work going on in Oxford particularly actually, that my collaborator Phil Saw, who does autonomous scene segmenting. So trying to work out what objects are, what's a chair, what's a person, what's a bike. Particularly this feeds into autonomous car work, because you've got what's the road, what's the pavement, things like that. So there are other systems emerging in order to try to simplify the world into objects. These still require very large computers, a lot of pre-processing work, and again, they're not, that kind of image can't be reduced into a display which someone who's only got very, very limited sight can see. One of the key features for visual impairment is you lose contrast sensitivity. So the number of things you can see at a single time drops right down. So, and is that what people want? So where we kind of went to, we've got a scene like this. You've got a person, you've got a couple of partitions nearby, and you've got 2 people there. As we're trying to think about how we do this, the Xbox Kinect came along, which is a game-based camera that looks at depth rather than anything else. It uses structured light, essentially produces an infrared spectrum, which another camera picks up and looks for the disparity. With that, you can produce a 3D image. So you take that same picture and then construct it as the actual depth to the particular surfaces that you reflect. And that means you can start to pull apart some of the aspects that are in front of you to make them obvious. And I really just started with a very simple thing. It's like, if you want to make something which is going to be useful for people who've got very little sight, and you can't tell what those objects are, my first guess was really just to say, well, the things that are nearest, at least in terms of walking, are the ones that are most important. Right now, over the next 10 seconds, I don't mind if that door's there, if it's open or anything like that. But I do mind that there's obstacles just here. So if I can show people that, I can start to build up their understanding of their environment around them. So what we do is we take that 3D image, turn it into, at least at the beginning, just turn it into a brightness display. So nearby things become nice and bright. Their shapes preserved because we've just constructed them from the 3D image. And that's something you can simplify down to a very, very easy way. You only need a couple hundred pixels if you want to represent that. The person here is nice and close, there's the next another person here. You can, with the system that we have now, we can push all the way back to 7 meters. And it really is, the limit is how much the person's contrast can really take it. Some people have only got perception of light, so they'll only be able to tell that there's, actually maybe probably not in this room at all actually, be able to tell often there's a window open, it's bright. And they'll be able to tell the orientation of that. Those type of people aren't going to be able to tell the subtlety between these 2 people, but for that you just pull it right back and you go even further. So a nice bright object is very near, you get round that, essentially you've got a safe path here which is black, and you're able to walk now with using your intuitive sense of sight, you're able to walk quite clearly through and around, avoid obstacles in the first part. So in order to test that, we built a highly aesthetically challenged wearable display, but it had a depth camera across the top, and because I didn't know enough about blindness at that stage, we've got this large bank of LEDs, and I think it's 12 by 8 for each eye. Because blind people can't see very much, they get a lot of light in. That story is basically me understanding how much people can see. If you call it that. Essentially, a pair of ski goggles you can put on, and when when passed in front, it got bright. So it looked a bit like this. So there's us in the car park testing it out. So nearby things are bright. So there's nothing in front, then it's safe to walk. And my colleague Ian walks across in front, and there's only 15 or so pixels representing him. But what's quite nice, because this is a live video running 30 odd frames a second, we're so tuned to seeing what people look like, stereotypical behaviour such as waving arms, that it doesn't really take much at all for you to understand that something's a static pole, something is, we can't really see cars in this picture, but waving in the hand is something that's really easy to transmit because we're all tuned towards that. And in a sense, this is one of the things that's lost by other forms of visual substitution, such as auditory or even canes, because you just don't get that same visual feedback. You don't get to excite the same parts of the brain that have learned over the last 20 or 60 years to see the world in a particular way. And if you simplify the world in a nice, straightforward visual scene, then you can be quite, you can respect the history of the person, what they've been known, what they've experienced, and allow them to be more independent. We ran some, this is a couple of years ago, we ran some very simple navigation tests. This was a couple of controls getting to walk down a randomly changing maze like this and show that it didn't take very long for you to increase your time. Collisions went down and velocity went up, things like that. So it showed that you could, even with such a crude display like that, you could learn to see what objects are like. We tested this with some visually impaired people. We didn't get them to walk around because it was too early for us to throw people in such a crazy device, but they were able to see things at 4 to 5 metres away, see their own legs, even with such a crude image. What we did find out is that many people were saying, oh, what's the gaps between these legs? Is that important? And realised that the resolution of a wide number of people who were sight impaired was much, much better than we expected. So we designed this one. This was now the beginning of midway through 2012. It has OLED display similar to an old style mobile phone, and the depth camera of the other one but paired back. This time, rather than mounting it on the ski goggles, we put it onto a very kind of crude, sort of tortury looking headset next to a laptop at the back. Because ultimately, we wanted to run really efficiently, but until that stage, on laptops. The inside now, we're looking at about 20 by 12 pixels per eye. So stepping up gradually, partly because we couldn't get it running fast enough to make some sense. And this was able then to show much more interesting things. So here's the walls on either side of the corridor, and here's Tom in the middle doing some waving. Now it looks like a low-res video game, basically. It's binocular, so you fuse these two together to produce a quite comfortable visual field. Primarily what we're looking for is obstacle avoidance, so that box on the ground pops up against the background, because simply if you translate distance into depth, nearby things become very bright and you find trip hazards. And what's extra nice is this is carrying its own light source, so you can walk into a dark room, so the seminar room near our offices, which the camera's not being able to pick up, but here you can see chairs and tables, they're popping up as objects basically. One of the things that we hadn't done at this stage was manipulate the floor. So the floor still comes up as a bright object, and if you turn down and face it, your entire field of view becomes illuminated. But nowadays what we do is we just fit a plane to the floor and delete that from the image, which means that you can show small objects on the ground very clearly. And it actually took a long time before any of our participants actually noticed that there was no floor anymore. They'd seen the previous ones and they go, but no, it's not. You just trust the floor's there. And in fact, by fitting planes to it means that you can detect changes in the floor much better. So stairs pop out. Everybody's been working recently on one which we put off for a long time, so we didn't know how to do it, but showing the stairs going down. Obviously that's a real issue if you're not sure of that. But we can detect them basically as values that are beneath the ground plane, and we just make the whole thing flash. It's a bit crude, but definitely gets the point across that there's stairs there. Or a well or something. Not that you come across wells very often. If you did, it'd be great. One thing I think is worth noting at this stage is that these displays were right next to the eye, so the same position as glasses, but there's no optics on it, there's no focusing apparatus at all. So it's always a blurry image. In fact, it's really, really blurry. But again, this is me learning about visually impaired people. It was never a consideration because we were looking at people who have only got the very basic levels of sight, really what you call hand movements. So you can tell hand movements, occasionally you can count fingers. To be honest, that is how optometrists and ophthalmologists rate sight loss when you get all the way down. It's like, well, can you see my hand? Can you see my fingers? Because there aren't really that good scales. Also, there aren't many things you can do. So can't live with that. So we didn't worry about doing a focusable display because it was overkill. It was actually technically quite hard. So we left it at blur again. Really, nobody did it. But now we're starting to expand that a little bit more. We're looking at focusable stuff, and I'll talk about that towards the end. But it did mean we could get where we want to go in a very short period of time. So we tested this out with a bunch of participants summer last year, just like you recall, which in hindsight was a terrible place to do it because it's full of high visibility lines on the ground. And another thing I've learned about visually impaired people is that you use all sorts of cues. If you've lost your primary sight, you'll find reflections on everything, small regions of light and shadows in front as things move in front. It all just becomes part of your visual repertoire, and sound is huge. So high visibility lines are, they're a problem, but it was too late. We'd already set these up. We just recruited widely from the local populations. We didn't really mind who we got, which particular eye condition. We just wanted to get a lot. And set up this 15-metre runway. In fact, there's another one over here. We had to walk through curtain doors, but it was a bit weird. Essentially, had to avoid these obstacles while wearing our headset. Now, this is one of our favourite participants who's got very, very low sight. She's got retinitis pigmentosa that I mentioned before. She just has 2 islands of sight, which are just up at the top right and top left-hand corner. She uses the guide dog, and she doesn't really consider her sight to be much use at all. So, and she's very nice, so she doesn't mind bumping and stuff. In fact, we made everything out of foam, so you can kick her around, something like that. As she walks across, you'll see, even in relatively good light, she completely misses that. But she tells it off from being in the wrong place, so she doesn't mind. This one does fall into a field of view, so she's able to see that fine. But things in front really aren't able, she's not able to do that at all. Now the next one, when we put the headset on, it'll be slightly darker and you'll see like a little shadow of brightness coming around, which is the infrared light from the camera, but that's not something it does. So now she's standing here in front, we've got a number of obstacles in front. For the first couple of meters she can't see anything, but then once she gets nearby, she's able to detect it very easily. And in fact, even with that crude resolution, she can still point out individual objects. Even though they're relatively close to each other, they don't blur together. And there's a third one there. And then she can make a safe path around it. You will notice, or maybe you did, maybe you didn't, there's a caution to how she walks. It's a strange way to see the world. So it's not, the research isn't done. It's still learning how to get this right. Another example is to show you that's happened more than once. So, I mean, the walking speed is an issue. It is something we need to think about. But as the environment gets more and more complex, she's able to navigate around. And this was, we tried this with and without the glasses, a range of different people, and found very common, very good responses to this people. The basic response really is it's very quick to learn. This was one of the primary things. But you've got your visual cortex intact, and you've got the desire to see things. So we expected this to be very, very simple, overly simple in some respects. So being able to detect there's an object in front of you and finally detect that's a person is 5 to 10 minutes really. Walking around with some degree of confidence doesn't take very long. Accidental contacts, another thing that really drops down. Almost no one collided with an object once we had the headset on. But one of the standard ways in which you rate assistive technology is preferred walking speed. So walking unaided, so you tell the person there's nothing in front, walk as fast as you want, would be your 100% preferred walking speed. Unaided, there's a drop in the group, and then with that, we'll call them the residual vision with glasses. Drops it again. So there is definitely a challenge there in terms of making it not just intuitive, but making it something you can really trust. And maybe I'm being a bit hard. People like you had used these for 30 or 35 minutes at a time. So they didn't have a long period of time. They weren't using it for days. They weren't learning how to take this information in and really make it their own. So So perhaps over a longer period of time, people would become more confident. But really where I saw the downfall, or at least the shortcoming with this particular version, is that it didn't allow any other light to come in. As you saw in the video, all we were showing was our computerized display. Whereas most people have some vision, either central or peripheral, which they would normally be using to navigate. So what we needed to do really is to allow them to see the world as they normally do, and then add our obstacle detection on top of that. Before I do that, there was another nice analysis that we were able to do. So here's a person walking their path through the obstacles. Now, one way you can look at it is the distance they are from obstacles before they collide. So it's like a deviation distance, if you will. So I'm walking up, a normally sighted person will be looking at sort of 4 meters or so, and they'll veer away, depending on the crowd, things like that. Someone who's not able to see anything will go right up to it, like 1.5 meters, and they'll be basically touching it before it'll pop right up at the end. When you look at all the people that we tested, and you can rank them actually in terms of people who are fully sighted or partially sighted. Partially sighted means you probably can't read or recognise faces, but you're generally right to walk around. All lower ones, like perception of light, hand movements, or counting fingers. People just rated it in terms of their unaided condition, how close they were to obstacles before they had to deviate away. So the people down this end were getting right up next to it before they moved away. People up here, the sighted people are obviously just veering at their leisure, a long time before that. Now, if you compare that to their deviation distance when we put the prosthetic glasses on, you get quite a nice effect. The people at the lower end of sight, people who really were getting right up to it, we're getting a boost in the distance in which they can detect objects. And people who were great at it got a serious deficit. So they were all pulled down to roughly the right level, or roughly the same line, which was quite close to the limit of the detection for the camera, which is between 3 and 3.5 meters. So people weren't able to see further away than this, and basically meant that everyone was behaving roughly the same. It was a real leveler. What was quite nice is it helped show the proportion of people, as we sampled quite widely, the proportion of people who would be able to help with such a crude display, which is really, in this case, the bottom third, as we'd expected, people who've only got the serious limit to sight impairment. But it did emphasise that what we need to do is build transparent systems. So the ability to be able to see the world as you normally do, and overlay information on top of that as a proper augmented system. So essentially that's what we've been doing ever since this study finished. It was always the way we wanted to go, to make something transparent. Mostly for me it was because it was going to look better. Everyone could see each other's eyes and you wouldn't feel cut off from the world. But the addition of the transparency allows you to add those two together. So we've now made several versions. These are different ones. These use transparent OLED displays. So fortunately, there's almost no market in the real world for transparent screens. Lenovo made a transparent phone, which is just obviously when you take it outside into the sun, it's just useless. You can't see a single thing. And when you get the camera on it behind, it's just really weird because you can see through it and see the camera. So anyway, the people who made the lenses offered them for sale, so we bought a bunch of those, made these cool glasses. And this one is actually the one that we're testing. So it's the same transparent display, slightly a dark medium in front in order to produce the contrast, but you can still see straight through it. And a depth camera mounted across the top. So we're not actually worried too much, because we're research rather than product manufacturing. We don't worry about shrinking stuff down to make it sellable yet. We're really interested in terms of trying to prove the principle right and then take it on to the next stage so we can start making these or start selling them. So you can use your remaining vision and it's going to be slightly nicer. There's been a nice development lately by Epson. In fact, Google did this with their Google Glass as well. Making transparent glasses that actually have, you can't see them here, but actually you can. That little square there's one there, is a transparent mirror called a beam splitter. And there's an image being projected across here which will go right in front. And it produces a display which is about 35 degrees in front of you. It floats there. It's a bit smaller than we have for our normal displays because it doesn't show you a wide field of view, but you can put a lot into that. And it's much better for people who have got low vision. So rather than people who are way disadvantaged, it gives you a lot of information about, you can squash all your peripheral vision down into there and you can produce sharper lines. We've started to work now actually in all these areas. So So after polling what people really need, in fact it really takes half an hour with half a dozen people to work out really what visually impaired people want most of all. All of these have now become quite doable by us or our collaborators in engineering. And the particular ones is face detection. And we've built a system to identify faces in the environment and hold it still and make it very large on your entire display. And that works very well. It's very computationally, very, very simple. And we can fit that onto these glasses. So this is them in their nicest light. They're actually quite a fair bit chunkier when you actually put them on and wear them. But it does allow you to bring up faces. It started some work on reading assistance, which is the toughest of problems, but it's worth attacking. They allow people to read with their peripheral vision. But I think what's been quite nice is this object learning and recognition. And the Royal Society gave us some money to look at learning objects, particularly signs, but eventually personal objects, and allowing you to detect them and track them. So you get your system in basically I don't know if anyone comes from a computer vision background, but you essentially build templates of an object from as many different angles as possible, and then you scan a picture for any of those templates. Once you've found it, then you can track it, you can simplify it. And it's actually not that hard to do, as long as you don't have too many objects you're trying to track. And that's quite useful for lots of people, particularly for recognising signs and directions, getting around public transport hubs, which is a key part. So we've got a project which is looking particularly at detecting navigation signs, learning them, and allowing people to get a bit more mobility, a bit more confidence in terms of finding their way around unusual places. So that's the main direction for the next 6 months. So let me conclude, I guess, with that. The first thing we set out really to do was do this depth to brightness display, and we've been able to do that in a number of different forms, and start to get a feeling for the parameters, how rich the experience has to be for people, and fractioning off what type of people this actually helps. Turns out we probably help about a third of people who are registered blind, which is still 100,000 in terms of sheer numbers, but the actual people obviously who find out about it and get out to do it would probably be a tenth of that or so. The actual practicalities of obstacle detection is quite easy to do. It's easy to learn and it's quite effective for people. Really what we'll be able to do is make these and sell them. Now, as I said before, there's stuff on the market which is many £1,000s, but all the devices, all the things you go into here, even these glasses themselves, if you buy them off the shelf, they'll be available in June. They cost about €600. That's for an individual one without any kind of partnership or support or getting the guide dogs to support anything like that. So that's not. The camera won't be good enough for obstacle avoidance, but the basic hardware is becoming completely affordable now. So we should be able to make something which is actually a lot less than that, particularly if we get charitable support, to be able to produce something which is going to be closer to a couple £100, which is much more achievable for people who are who don't have a great deal of money to throw around. There's already enough people in the area for assistive technology getting a lot of cash out of people who don't have it. So I got paid to do this work and I enjoyed it, so I'll do it for a low cost from now on. And finally, the project continues to stay interesting, because once we've got the right idea about how to get people around and avoid obstacles, but there's so many things you can add on to it. The number of people who have asked for face recognition, so not just showing where a face is or expression, but actually finding where their friends are, is huge. It's probably at least half the people I meet want that. And the key thing is that you miss out. You go into a room, you miss out on social interaction, or actually, because it actually is relatively hard to tell if someone is registered blind, because a lot of people don't want to let on. They won't carry a cane. The stigmatising in a sense. A lot of their peers don't know how sight impaired they are, so when they're waving, from 10 metres away, and the sight impaired person doesn't see them, it's got some negative valence to it. So if you're able to find that person, detect their face, and report that auditorily, presumably, then you would be able to help out a lot of people without using basically the same techniques that a camera or Facebook or different things like that will do with face recognition. So it's very worthwhile aiming to do that. And I mean, as we go through, as more people come up with different techniques in terms of computer vision and robotics, we can start to incorporate those. One of the problems is you never want to try to overload a system and make it do too many things. You can do a couple of things really well. But you know, it depends on the level of sight and how willing a person is to try out technology and see what they want to do. So that's a summary of my work, what I'm doing. We'll be continuing that for the rest of the year. If a couple of grants that I've got in work out, we'll continue that for a few more years after that. And the aim is really to be able to produce some kind of product, potentially an early one at the end of this year using the glasses that I showed you before, but more likely midway through next year for something which is actually going to get people really enabled. Thanks very much for your attention.
Right, guys. Do you have any questions for Stephen?
The tea's very warm, so it's very fast.
Colin.
Facial recognition is quite hard. An alternative would be something like caricature. I'm thinking of something like this which has been done with neural networks.
Yeah.
So knowing the average human face shape, just make it much, much more different from average. So you let the user do the work beyond that. Have you already been thinking on those lines?
Yeah, it's something we'd thought about because when we're looking at how much data we can put into a small screen, we realise that a lot of the elements of the face are pretty, they're not going to add much more than just like the distance between the eyes and particular shapes. So we have a collaborator down in Australia who works in doing the computer vision component for retinal prosthetics, and they've got very few electrodes, so they're really keen on caricaturing. And just really it's just a case of, I have to check if their model's the same way that what you described, but they do just enhance. I always thought you would actually try to almost cartoonize it, make it very, very high contrast. But they've been able to show that even with a very limited array, if you accent certain features of the face, it makes them much more recognizable. I thought about something along the same sort of line for expressions. If you, all you have to do, you detect the faint bit of a smile, and then you exaggerate it on